Alright, this is problem number 7, and if I had to pick a problem that it seemed to be the most difficult, this would be the problem. And the reason I think it is the most difficult is because it uses real data, it is a lab-based question, and unfortunately, every single AP test since the College Board has begun to put them out has a lab-based problem on them. So you need to become very familiar with these problems and get very comfortable with interpreting data and using that interpretation to answer questions. So let's look at this problem a little more closely. It says the following: a 50 gram super ball is thrown horizontally in the negative x direction against a brick wall, so that it bounces directly back after hitting a post. The vertical motion of the ball during the throw is negative. The horizontal position of the ball's center of mass is a function of time as described in the data table below. What you're plotting is the ball's horizontal position as it moves towards the wall and then away from the wall as a function of time. Now, if you look right down here towards the bottom under the graph, something that you all need to keep in mind is we always plot y versus x. Therefore, we are given position and time data. Position goes on the y-axis, time goes on the x-axis. Make sure that you label your axes with what it is and the appropriate units. If you don't do that, they take points off. Now, let's put some points on this graph so that we can get somewhere. So, first point, 0, 25. So let's make some tick marks on this graph so that we know what we're looking at. So let's say if I make everything 2, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 25 is going to be at the top because I ran out of space. So, at 0, we are at 25. So we are all the way up here, and that's 2 seconds. So let's say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, etc. So this is broken up into 2, 4, 6, 8, 10, 12, 14, so on. And our x-axis is also broken up similarly. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, etc. Now let's plot our values. At 2 seconds, I am at 20. So 14, 16, 18, 20 here. At 15 seconds, excuse me, at 4 seconds, I am at 15. At 6 seconds, at 10. Eight seconds at 6. Those are milliseconds, by the way. 10 milliseconds at 3. 12 milliseconds at 2. And then we begin to come off the wall and bounce back. So 14 milliseconds back to 3. 16 at 6. 18 at 10. 20 at 14. 22 at 18. And at 24, we are at 22. which is up here somewhere. Alright, if we connect that with a smooth curve, okay, it looks something like this. Beautiful. Now, that's the graph. Now we have our data plotted. Let's move on to part B. It says determine the ball's initial velocity before coming into contact with the wall. So if we remember something, and this something is exceedingly important, alright, we're looking at part B. We are asked to find the initial. We are giving no information except for this graph, so we have to figure out and use our brain to think just a little bit about what we know. Don't overcomplicate it, just think about it. So, we should remember that velocity equals change in position over change in time. Okay, this should scream at you, slope. Now, we need initial velocity, and if you notice, initially, this line here, right here, has a very constant slope. If we assume that that slope is indeed constant, from beginning until roughly about where I ended my circle, we can take the slope of that line and we can get an initial value. So, let me do that. So I have V equals x final minus x initial over t final minus t initial. Again, this should look very familiar. y2 minus y1 over x2 minus x1. It is slope. There is no difference. Let's plug our values in. The points I will pick will be 25, 0, and 22, other way around, whatever. So 20 minus 25 divided by 2 minus 0. That is negative 5 over 2, or negative 2.5 centimeters per millisecond, which equals negative 25 meters per second. That was it for that part. Now let's look at C. C says the following. Determine the ball's final velocity after bouncing off the ball. Same idea. Same exact formula, same work. V equals x final minus x initial over V final, T final minus T initial. The only difference here is we are now looking at not the beginning of the graph at 0. We're looking at the end of the graph from about 18 seconds to about 22 seconds. Again, that line is relatively straight, so I can assume that slope is constant. So I will take that slope and work with what I have given. So if we look at that, we have 22 minus 18 over 24 minus 22. That is 4 over 2, right, which is a positive 2 centimeters per millisecond, or positive 20. That is D. D says, what is the ball's average acceleration during the time period when the ball's velocity is changing from 6 to 16 milliseconds? So I want A average at t equals 6 milliseconds to 16 milliseconds. Now, if we think and we use the information we have already found in B and C, okay, we have to remember our slopes are relatively constant at 6 milliseconds and relatively constant at 16 milliseconds. So, remember what we know. Velocity at 6 milliseconds we found in part B was negative 25 meters per second. And at 16 milliseconds it was positive 20 meters per second. Okay. Now, using that information, A is simple. A, average, is change in velocity over change in time. Okay, V final, that is 20, minus the initial, negative 25, divided by a final time, minus initial time, that is 45 meters per second over 10 milliseconds. Right, do a little bit of unit conversion, you get 4.5 times 10 to the third meters per second squared, or 4,500 meters per second squared, however you want it. Lastly, part D. Or excuse me, part E, I apologize. It's getting late. Part E says to determine ball's instantaneous velocity at t equals 10 seconds. So V instantaneous at t equals 10 milliseconds. So if you will allow me to draw kind of a basic picture, very, very simple picture for you, just to bring your attention to the graph. A graph kind of looked like this. 10 milliseconds on our graph was kind of towards the bottom, right about here. And if you remember, V instantaneous equals dx dt. This again, remember, ladies, I told you, do not lose sight of the big picture. What are you doing when you take a derivative? You are taking the slope of a function at a point. That's it. It's that simple. Don't make it any more complicated. In other words, take the slope of that line right there. Okay? Find slope. Alright, so if we use some points, okay, if I had the graph in front of me, it would look prettier and the points would make more sense, but you're just going to have to believe me. If you don't, do it yourself, and I think it will make perfect sense. So the instantaneous is the slope of that tangent line to that position versus time curve at t equals 10 milliseconds. So what I have is x final minus x initial over t final minus t initial. That is, I chose the following points to calculate my slope. Therefore, I got roughly a negative 0.83 centimeters per translates into approximately negative